Good afternoon, everyone. So I'm Mingli from the University of Hong Kong. So Yuen is my supervisor. He's now in the university, in Monash University, and Kwan is a team member. So I'm glad to introduce our paper, O-ring and K-star, efficient multi-party private set intersection. Okay, here we go. The outline of this presentation is as follows. First, I will introduce what is mPSI, multi-party PSI, and then I will introduce two preliminaries, the Oblivious random function and the Oblivious Key-value Store. And then I use these two preliminaries to build two mPSI protocols. And then I will show the experiment results, and then I point out some insecurity, the insecurity of some previous works. Then I make a summary of this presentation. Okay, first, what is mPSI? So there are n parties, so each one has a set. So the goal is to computate the intersection of these parties, and the P1 will be the protocol receiver to get the intersection, okay? So here, the security requirement is that no item in the section I is disclosed to the adversaries. So when we move from the two-party PSI to mPSI, the greatest challenge is collusion attack. So now we assume that there are T colluding parties. We denoted as C. If the protocol receiver P1 is in the inclusion, okay, then the colluded parties, they can only learn the intersection, okay? If P1 is not in the colluding parties, they can learn nothing, okay? That is a very challenging thing, okay? Then I will introduce the preliminary. The first preliminary is the Oblivious random function. So here, there are two parties. One party is the sender, the other party is the receiver. So after OPRF, the sender will learn the OPRF key, K, and then the protocol receiver will input a set and get the corresponding OPRF values. So after the OPRF interactions, the sender who gets the OPRF key can compute any value, OPRF value related to a key. So it's very easy to use the OPRF to build two-party PSI protocols. The sender who gets the key and can compute the OPRF value set and directly send it to the receiver. Then the receiver can computate the intersection based on the OPRF values. Okay. Then we have the second one, Oblivious Key-value Store. It is a data structure. Okay. There's two phases. The first phase is encoding. Okay. Now we have a key-value set. By utilizing the OKVS, we can use it to encode the key-value powers into a table T. So the table T will contain the shells of the values. And then we have the decoding phase. So if you input a key, so if this key is in the original set, the key set, you will get the correct value out, but if it is not, you will get a pseudo-random one. So by utilizing the OKVS, we can have our first design. So here, there are n parties. The first party, they can generate pseudo-random value for each item. Then we have a key-value powers. Okay, then we input this key-value powers and to get the first OKVS table, and we transit it to the second party who has the input x2. Then x2, after decoding, p2 will also have a key-value power set. So after this transition to the final party, Pn, Pn will also get the key-value power. So the quick takeaways is that this construction can be a filter to filter out the non-common items. Okay, because of the property of OKVS, only the common item value keys can be remained, okay? So this structure, we call it OKVS chain. So here, we exploit the OKVS chain to give a very naive design of mPSI. So P1 just do masking with P2, and mask is by sharing a PRF CS. So both P1 and P2 will compute PRF value, a common value, PRF value if their items are common, okay? So have this construction, we can easily find that after P1 gives values to P2, then can transit this value to P3 and then until they get to Pn, and Pn return the value to P1. If there are any item in the intersection, the same value will be transited back. If there's no common items, then P1 will get a random one. But though this ring design is very naive and simple, there's a risk for the brute force attack. Imagine that P1 the input domain is small, so P1 will easily to enumerate all the items in the domain. So it's easy for P1 to get the intersection from the P2 to Pn. So we do not expect this. So we have another design by using here we can simply add an OPRF between P1 and Pn. So because OPRF is usually directional, okay, only the Pn has the OPRF key. So P1 is not P1 cannot compute the related OPRF values, so it can be secure. So here, we give it for O ring T equals 1 because there's no collusion. Here, we move forward by thinking that if there exists collusions, for example, P2 collude with P4, then it's easy for them to know the intersection of P2 and P3 because P3 directly get the values from the P2. So if they collude, they can easily know the intersection between X2 and X3. So after we introduce a ring for T equals 1, we want to build a protocol that can be against the arbitrary number of colluders. Okay, here's our design. So first we need to have an assumption. P1, let's assume P1 is honest. So he or she will not join the collusion. So based on our above design, so P1 can do masking with P2, P3 until Pn-1. So after masking, all the values, so P2 to Pn-1, their values will be masked. So if other parties, they are colluding, so what they got is also pseudo random values, so they then cannot get anything from these pseudo random values. So that will be secure. So we move forward one more step. So we need to assume P1 is always, but in real world applications, P1 may not always. So then in that case, what are we going to do? We need to find another party who can take the role as similar as P1. So here, let's assume PB is the one that is always. So here, a slight difference is that PB needs to do OPRF interactions with all other parties. So why do we do this? Because by using the property of the OPRF, it is unidirectional. So if an atom is not in the intersection, so there will be a OPRF value that's not equal to any other value. So the value sum of PB will be pseudo-random to all the other parties. Then this common item will be non-common item will be secure. Then we combine these two designs by assuming P1 is always and PB is always. So we assume that the maximum number of colluding parties is T. So we have put aside P1. There we enable other T parties as the common OPRF sender. So among these two T plus 1 parties, there must be one always party who can take this role. So it will make the protocol secure. After I introduced the O-ring, which is a ring star, as you can find that, we can move forward to K-star by making a slight modification. So we, instead of using the OKVS chain from Q2 to Pn, we just break it, and then these parties can directly send the OPRF tables directly to Pn. So Pn can also compute the sum of the common OPRF values and the PRF values. Then they can get the intersection. This is the same for the case when T is 1. That is when there's no collusion. So we compile the O-ring and K-star. So O-ring, as the name shows, is ring design. So the OKVS tables need to be transited sequentially from P2 to Pn. So compiled with O-ring or in K-star, so all the other parties, they can directly transit the OKVS table direct to Pn, so Pn can do that work. So for the ring star and the ring structure and the K-star structure, in K-star, there will be a center. The center will show the largest workload. But in O-ring, so the parties will show the workload. So here's the experiment result. We can see that from this table, our protocols, O-ring and K-star, outperform others in most of the settings. Okay. And in the communication course, you can also see that it outperforms others in more settings. Adjust. So I will also introduce the why some existing protocols are insecure. Okay. So though they come from some big conferences. Okay. So for example, the augmented semi-always mPSI in KMPRT from CCS 2017. So there are two steps. In the first step, so each party will share a common PRF seed with other parties. So they can share the same, since they get the same PRF key seed, they can compute the same PRF values. So the same OPRF values, the sum of them will be 0. So the final result will be 0. So in the second stage, they have the OPPRF with P1. Then P1 will add all values together. If the value of one common item is 0, they deduce that this is a common item. So that is how they build their protocol. But this protocol is insecure. Like what I just mentioned, only the item in the intersection can be disclosed. But by utilizing their protocol, this is not the truth. Okay, let's show one simple example. In this example, there are 5 parties. If P1 collude with P2 and P3, so in the first phase, P2 and P3 can directly send all the PRF seeds to P1. So P1 can compute at the PRF values for any items. So it's easy to P1 to get the intersection from with P5 and P4. Okay, but X may not be in the set of P2 and P3. P2 and P3 they just directly send the PRF6. They cannot even join the intersection computation. Okay, so though it is efficient, but it is insecure. So there are also protocols based on this protocol. For example, the NTY 2000 NTY from CCS 2021 and the GPRTY from Crypto 2021. Their protocols are built on this protocol, so because of the same issue, their protocol is also insecure. Okay, then in KMPRT, there was a specially proposed three-party mPSI protocol, but their protocol also has the similar issue. Okay, so here our protocol is secure. Why it is secure? Because it is each party is a common OPRF sender. Okay, nothing beyond that will be closed. Okay, so let me give a quick summary. So we propose two efficient mPSI protocols, and then it has wide applications. In our paper, it will show more figures about this. And then we implemented the OKVS. We made optimizations about it to improve the computation and to reduce the computation cost. Finally, we identify the insecurity of PRF. I'd like to answer the questions from the audience. Thank you.